more interesting. So the title is nice here. The color scale here is actually vorticity. So red is positive vorticity and blue is negative. So this thing here is actually a large scale vortex, and this part actually comes from the simulation. And the whole talk is about how to form this vortex and their properties. Okay, so well, I guess people don't really like 2D turbulence because people always say it's not real. But that's okay. I guess I will argue that at least in this film, you can more or less see 2D turbulence. And on the the atmosphere of the Earth, well, you can say it's really 3D stuff, but somehow you can integrate over the scale higher, and then you come up with some 2D equation. You may have some extra terms, but the fundamental thing is still in the 2D Laplace equation. And this is just a cloud from Jupiter. So this is the type of system we are talking about. So this is Kelvin temporal instability. At the beginning, we have a really thin layer of vortex sheet, and that becomes unstable, and you see this the vortex start to merge and form bigger one. So, and this is actually a simulation that's 4,000 square time on the GPU. Okay, so go to the equation. This is the 3D dynamics equation we're solving. So U is velocity, that's the nonlinear term, the pressure term, viscosity. So this is a damping term, people call it Ekman friction, and then that's the forcing. So the pressure is solved by the divergence condition. If you take the curl of this equation, you end up with a scalar equation. So omega E is vorticity, you just follow your velocity, and again you have viscosity and Ekman term, and then the forcing becomes like this. If we drop everything on the right hand side, so if we remove viscosity, Ekman term, and the forcing, then the total energy, which is defined this way, and the entropy, they are conserved quantities. Okay. And using this conserved quantity, you can now argue that if the energy flux is a constant and the entropy flux is a constant, you will have two different power laws. So you will have two different inertial range, unlike 3D turbulence. In 3D, you only have one inertial range that's k to minus 5, but in 2D we have two. So the energy inverse cascade to large scale, that's minus 5, and the entropy directly cascade to small scale, which should give you minus 3. But this is actually steeper because you see the dissipation kicks in. And I should also say this spectrum is done with a calculation with the Ekman term. So there's nothing special happening at the large scale because the Ekman friction is able to remove energy when you inverse cascade to large scale.
The dashed line has which slope?
So this one is minus 5, this is minus 3, and this is minus 5.
Yes.
Yes. And the forcing is at here. So I think for this simulation, the forcing is, I can't really see it, it's probably 64, something like that.
And the energy injection was at 60, yeah, or something?
64, probably.
And if you do it at, say, 8,
Yes.
do you get it closer to minus 3?
Well, I guess it actually depends on the viscosity and all those things. Yeah, but if you make the viscosity small enough, then it's closer to 3.
And it also depends on the Ekman friction.
Yes.
In direct cascade, your exponents are not universal.
I see.
So they depend on the Ekman friction.
Yeah, I see.
Okay.
So for smaller friction, it should be okay, right? You should get closer to minus 3.
Possibly, I'm not sure. Possibly, yes.
So this is the spectrum, and we can just look at the actual simulation. So this is again 2D turbulence, but so this forcing is a constant forcing called Kolmogorov forcing, and you develop this channel, and then the channel break down, and you see all of these crazy eddies. And the next simulation. So So this is the random forcing I actually talk about in the spectrum. So yeah, you pretty much see the same thing. Your forcing gives you some energy input, and then you form a lot of energy, and you kind of see these vortex find each other and merge.
So still plotting density here.
Yeah, this is also vortex thing, the type. So red is the positive one, and then blue is the negative one. So this is fashion because the resolution of the movie is too high.
Even I can see the inverse cascade.
You can more or less see the inverse cascade, but this is not totally clear.
Yes.
And the reason is because there's an event trying to remove energy for the large scale. So now the problem we are interested in is what happens if we take away the event time. So we will remove the large scale friction, and now so this is the simulation without the large scale friction. And if you're patient, then you can see some of these big vortex start to form. And this thing actually takes a long time, and that's the reason we only do it in much lower resolution. Now, so the rumor here is when you don't have the regulation at large scale, then the solution will eventually blow up because you just keep pumping energy into your system. But so actually earlier this year we went to Santa Barbara, and John Bowman told us that that's not the case. That's because, well, no matter how small your viscosity is, when you have a lot of energy in your largest scale, you can always remove enough amount of energy so that your system can saturate. And then so at that point, just say then it should be the viscous time scale when it saturates. So that's the reason we start looking at this problem. Okay. So the code we are using to work on this problem is actually a GPU code. So and it's a spectral galaxy method. So the nice thing about spectral method here is, in the ideal case, if you do not have viscosity and resistivity, the conserved quantity actually preserved. So so that's a nice thing to have. And then we implement this with CUDA-C and run this on GPU. And the reason is it just takes too long for the thing to saturate. So we want to have something fast. So GPU is actually about an order of magnitude faster than CPU. So we use that. And right now this code is already on the Google Code, so we can just download and look at it. So this is just a single slide introduction to the GPU. So this is the card we are using. So it's a Fermi architecture based called Tesla card. So the reason this graphic card, the reason people start to be interested in this graphic card is because they are just really, really powerful. So at the beginning, when people just this graphic card only to draw stuff. You can't really do a generic program on that. But as the architect you can do much more fancy thing on that. And yeah, so as I already said, the performance is usually an order of magnitude faster than CPU. And the reason for that is, for CPU, you actually waste a lot of transistor to do all the control. So for CPU, the caching is automatic and things like that. So that actually wastes a lot of your transistors. But for GPU, you don't have that. All of your transistors are used to do computation. So the advantage is faster, but then the disadvantage is now the programmer needs to work harder to make this one, because the GPU is not going to manage the memory from it. Okay. Yeah. So instead of thinking about your multi-core CPU that has 4 core, 6 core, the GPU actually has much more than that. I think the typical number is like 24, 60.
65,000.
No, actually that's not the number of cores. That's the number they want to launch first.
Yes.
And that's to high latency. But anyway, so the main idea is, instead of writing a for loop to do your computation, you just say you launch your job simultaneously and do everything together. So, and I think we have time, so I can do a demo here. So let me first log into a GPU machine in PDC. Okay, and now let me just download the code and compile. Let me compile it with single precision, because single precision is actually 2 times faster than double precision.
How many times?
2 times.
Yeah.
Yeah, but later on I will show you single precision is actually not good enough to do this condensate calculation. So now the code we finish compiling. So let's just run some test problem. So it will take some time for the program to start. But once it starts, it runs actually pretty fast. So the resolution I choose here is 1,000 square, and you see the code is running. And now if you go to another terminal and then you run IDL trying to visualize this thing. Trying to visualize the thing. Then you realize that the code is actually faster than IDL for the visualization. So the code can run about 100 steps, but then your IDL scripting will run for a transform to give you the code. So that's the difference we're talking about. Okay. So we run the code and we run it for really, really long time, and then this is the energy we get. So for different kind of viscosity, we have this different curve, and then the different style of lines represent different forcing scale. So as you can see here, when your viscosity is smaller, you actually saturate in a much higher level. So that's the thing as to saturate at the very beginning. So we want to understand this kind of behavior, so we come up with a really simple. Yes.
The green one, the lowermost ones.
Yes.
There is one of them actually goes into the red ones.
So this is actually not green, it's another color. So this is unresolved simulation.
Okay.
So what happens is this line should really go up to here. But then because the resolution we use is not high enough.
Yeah.
And as I told you at the beginning, for special code, your code is not going to go up if you are not well resolved. You will just get one answer. And I don't know if you can see here, there's another line here, the code like that. So this line should really corresponding to this one again. But then it go like that because you use single precision instead of double. So the run of error is not cumulative. You will see that more clearly in later pages.
You would call it E is infinity, but that's really only at infinite times, right? On the left hand, the axis, the y-axis.
Okay, you're right. So I should just use energy.
E of t is infinite.
Okay, so the way we do that is we first write down the evolution equation for the energy. So E bar here is the energy at the larger scale, and then these are the energy and the entropy for the turbulent fluctuation. So you can it's actually pretty easy to work this out. So F here is the energy input forcing, and your energy is dissipated by the entropy. And epsilon here tell you your inverse cascade will actually take away energy from your turbulence to the condensate to the larger scale. So now you have these equations, and you ask how can I solve that? So that's where the model comes in. So this is our model. We assume your forcing is here, and then you have inverse cascade of energy and forward cascade of entropy. So we just assume really simple broken power law for this turbulent fluctuation. And with this, now you can compute the relation between your energy, the relation between the entropy and another term. And then now you can substitute this relation into this equation. That's the model. And then now you can just solve for the saturated energy and entropy. Now, if now we use these two values to normalize our that's something else. So this is the spectrum actually comes from the simulation, and now we overplot this with our model. So you see our model actually makes some sense. It's not totally off. And now if we use our answer to normalize the energy, so at the beginning we have different curves, the scatter one different in location, and now they all collapse onto each other. So this curve here is the under-resolved simulation I talked about, and this one here, so this is the one for the single precision. So you see this go off. Okay, what else? Okay, now I'll go back to the spectrum. So this is the condensate, the large-scale vortex, and now you may wonder what is this peak here? Is that real? And our explanation is that. So now if you look at your large-scale vortex, and then you cut it like that, and you ask what is the shape, it's probably not just a sine or cosine. It's probably something more complicated. But something more complicated. Maybe something like that. So now you can say maybe the shape of my large scale thing I can actually y as a function of the vorticity at the larger scale. So that's it. It's y, a function like this. And if I do it like that, then f has to be an odd function. Right, because the vorticity can be both positive and negative. And if f is odd, and now you Taylor expand this. So let's call this f omega.
So what is it that we are plotting? What is the function of vortex?
You want to describe the shape of the vorticity.
So what?
So I just come up with a function to fit it, to fit the shape.
Then you can just make a sine plus, I mean the sine of the size actually of the vortices plus the sine if that's k.
So we already know this is going to be sine plus cosine. I'm just saying the vortex will have a shape that's more complicated than that. And now we ask you how can we describe that? Then we must have an odd function. So if the function is odd, then you can only contain this power when you take expand that.
But Drupa was asking, what is the quantity you're really interested in? This, one naively would have thought it's omega, not f of omega.
Yeah, so I should say the whole omega x1 is more as
Right, but now you write f of omega L, and what is omega L?
omega 1.
Omega 1?
Yes.
If, for the Fourier mode 1 indeed. Right.
And if I do that, then I will argue f only has these modes.
Uh-huh.
And now you look at the spectral space,
Yes.
and then you realize that the only modes you can occupy is these things. So these are the higher harmonics of your condensate, and this mode actually corresponding to this peak. So this is actually a real feature. Right?
Not all of them have one, there's a higher ones too.
So these four, they correspond to
Yeah,
condensate,
yeah.
so they have k equal to 1.
Yeah.
But then the next mode is square root 2 k1,
Uh-huh.
but then you cannot occupy that because of this. And then for the next, you can't occupy that either. So the latest, the second one you can have is here. So that's actually square root 5, which gives you
Yes.
6.
So what you are actually describing is actually the image, right?
That's what?
Is actually the energy spectrum.
Yeah, this is the energy spectrum.
Yeah. But I mean, you were at first still in 2 dimensions. Now
Yes, still in 2 dimensions.
energy spectrum is 1 dimension.
Yes.
Yeah, okay, maybe I should mention that when people do this measurement in atmosphere, they see the largest scale there is a -3 spectrum. So in order to match that, when other people do this condensate simulation, for some reason they also has -3 here. But now I'm saying I actually do not trust those plots because it seems to me they are just doing a different beaming. So if I beam these two things together, I will get something like this. If I beam these together, I will get something like this. And then more or less will have a power law over there.
I think when in simulation, at least when they look at it, they remove they take average and then remove the average. And when we generally look at the power law. You remove the condensate at K equal to 1 and then look at the power law.
Okay, so now if I just remove this, then what happens to this?
This I guess will be there.
Yeah, so I'm saying, this is just the high harmonic of the condensate. That's it.
But then the minus 3 is not coming from this 3, right? It comes from several trees.
Yeah, okay.
Anyway.
Yeah, okay, we can. Okay, so now we know the value of the saturation value of the condensate, but that does not describe everything of your condensate because you also care about the position. So this is, again, a movie of the saturated condensate. You see it move around, and if you trace the trajectory of the vortex, then this is what you get. Just pretty crazy. So, but now we can use the tele and say, if the vortex actually go through an edge, and we make the domain bigger and track it to the next domain. And now if we do that and unfold the trajectory, then we get something like this. So when you just look at this, you say, okay, it looks like a random walk. So maybe the condensate itself is doing a random walk here. So that's the reason we come up with another model to describe this movement. So the position of the condensate, it depends on some velocity, and then the velocity you need to damn it, and then with some forcing. And now if you do the standard thing and find the correlation, you will get something like this. And then you realize this is just a Brownian motion for massive particle. And then
Inertia, we should say, wouldn't we?
what is that?
Inertia, we should say, I think.
Inertial particle. Yeah, okay. And now, if you plot the trajectory of, say, 16 different simulations, so these are the dark gray lines here, and then you do an average, and this is what you find. And if now you fit the Brownian motion of the inertial particle, you will see you can fit it pretty well. So it seems well, I guess it's pretty trivial, but then this is what we do.
What's the inertia?
So you don't really need inertia here. The thing here is you want to get the time scale right.
Yes.
And we actually cannot derive the time scale. At least we haven't found out how to derive it. So right now we are just fitting that.
Yes, but from the fit we get a time scale, right?
With the fit then we get a time scale.
And what time scale does it corresponds to in this?
So
Is it something like large eddy turnover time?
so if so
Oh, that's something we talked about.
yeah, that's something we talked about. So previously I actually have a derivation that can show you the geometrical meaning of the viscous time scale and the viscous and the forcing time scale, something like that. But then later on I find out the derivation didn't make any sense. So we now we just say we don't know how to derive it. We just see. But okay, so I should also say this model is less trivial than it sounds, because when you do this, when you plot this thing, there are actually two parameters you need. So one is this turnover time when you go to Brownian, and the other one is the speed here. So the speed here, this part, we can actually derive it. And the way we derive it is we just look at the nonlinear interaction, and then we find out the dominant term is the interaction between the condensate and the fluctuation. So that we just use that to give us the velocity. And so the up and down, how do you call it, here. So this is not corresponding to fitting. The fitting is only the turnover location. Okay, so that's pretty much the result, and this is the summary. So the rumor is not warm, but it's just not too useful. So the way I see it now is actually it's the order you take the limit. So if you take the limit viscosity go to 0 first, then your energy will become like that. Then your system will eventually go on. But then this doesn't tell you too much. But now if you take the order in the other direction, in the other order, you take the order equal to infinity first, then you can saturate, and now you can ask how this depends on your viscosity. So I think this is the way I see it now. So this comes from our 3-scale model. So the condensate viscous time scale, well, 3-scale model can predict saturation pretty well. We just confirm this is Brownian, but we don't know how to derive the time scale yet. And then the GPU code is on Google code that you can use. So that's it.
Thank you. Yes, questions?
Yeah, so I say less than half hour.
Show us the separation equation again, or the E of T.
So I actually don't have E of T here, but I only have the saturated gradient.
Yes.
Yeah, so that's the.
You didn't actually give E of T. Did you give
So-
E of T?
So I didn't write it down here, so we can derive that, and then the equation is for ET. So that will be 1 minus potential, and then some time scale. Then time scale is 2 nu E1 squared.
So, where have you seen that last time? Ever seen?
Well, the simulation of the dynamo.
Yeah.
That's exactly what we get. Oh, what is it? The next one is 3k squared.
So it's you have a minus, it's minus T, and then 2 nu, so that's the viscosity, and then K1 squared.
I'm not sure, but
No.
possibly.
Other way around.
That way.
It's upstairs.
Yeah, you are.
Yes. So it's really just the same. It's large scale dynamos. Do we all know other systems which have inverse cascade behavior? So 2D turbulence is one. MHD helical turbulence is another. Any other example?
In immediate conference, you are not sure that it is actually inverse cascade, right? Because you don't know how local the energy transfer is.
Yes, okay.
But yes,
Do we know that in here you actually have checked that, yeah? In other words, that the spectral transfer at any scale here is constant, that epsilon is constant.
Yeah, so if you can plot your flux and it's more or less.
And we don't have that for MHD. Actually, that might be another good thing to get straight for before Frisch comes.
that's the helicity flux, right?
What?
That's the helicity flux.
Yes.
And that was what this guy, Shiv Kumar, was looking at. He was in Germany.
Yes.
That was part of his PhD.
Yes. And his result was that it is constant,
Yes.
but you had to look at the lower thing, right, or something like this. Was that what it is? It's only constant in the non-stationary case, I think.
Yes.
Yes.
And also, I mean, it's difficult to see what is the constant range from DNS.
Yeah.
One has to go really deep.
Good. Any other questions? Yes, John?
In your Ornstein, Uhlenbeck thinking, what I didn't see really what the structure of the potential was in your equation, but you can just tell me.
You mean the Thornton?
No,
It's
the
the
last
alpha.
slide, so the Ornstein-Uhlenbeck process.
Yeah, okay.
Yeah.
So
So
this one, it's just white noise.
It is. So do you check that the spectrum is red, or do you have any self-consistency for your argument that comes from simulations besides fittingness with?
So no, because this is only the simplest thing you can
Sure.
look for.
Yeah.
So if you just use a Brownian, then you cannot explain what's going on here. So next thing you try is this.
Yeah, because what I'm thinking is that you might get the different power law if the structure of the noise is different.
Okay, so at some point we are trying to look at this, but then the reason we look at this is we try to find out how to divide the time. But then we didn't get much.
Okay, so we should. This is something that we should talk about.
Okay.
Be interesting to talk about.
Okay.
Do you think, do you know, actually have an idea what happens in that case? It's red noise?
Well, so you get red noise from an Ornstein-Uhlenbeck process. It comes from the white noise in the
Okay,
and you
so-
get the power spectrum.
Yes.
So it's the basis of the fluctuation dissipation theorem. You get red noise
Yes.
out. So that's by prescription.
Yeah, so you're saying this is white, but then alpha is red.
Yeah. And so the way you make that assumption, you did your calculation, and then you fit this unknown time.
Yes.
In a way which is consistent with your assumption. So if you change your assumption about the noise spectra, then you can get a kind of multifractal structure which would give you different scaling exponents.
Okay.
That's all. And so that would be something interesting to
So
look into.
will you now say this is not Brownian? Actually. Okay.
Yeah.
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 I didn't quite listen correctly, I think. So are you saying that if the phi, you were saying phi should always stay white noise? Or are you now thinking you...
The definition of an Ornstein-Uhlenbeck process is that you are forcing your particle with white noise, and then when you look at the power spectrum of that, the power spectrum is red. So that's by definition this process.
Yes, so when do you now get multiscaling?
As you change the nature of the noise.
Yeah,
So-
right.
Right.
Yes, so
All
the
I'm
phi,
saying
yeah?
is, instead of, so you deal with the noise rather than dealing with this parameterization of the time.
Yes.
So you make it colored noise.
Yeah.
And if you replace phi by a telegraph noise, you still have, phi, here phi is white in time, right?
That's what I
Now,
understand. Yeah.
next thing I would do is to replace phi by a telegraph noise, but that will only be like thing. And then,
So we actually plot alpha in time to just see what's going on. So that's time, that's alpha, and that's time of the thing we see.
Yeah.
So alpha is not right. Not white. That's the reason we come up with the next thing.
Yeah. So when you detrend that and look for stationarity, so is there a cycle you can detrend alpha on and look for the noise on
Yes.
top of it?
So we also look at the spectrum. So I think it's something like so this is like is more close to the forcing time scale. And then this is something we are not able to divide.
I mean, I'm just wondering, is there a concrete, so we have our Brownian motion, which means we have T and we have, let's call it delta R, and then we have 1 and we have 1/2 here as the slopes. Are you then saying it should be different? Are you saying it should be, do you have
I can't derive the slope, I'm just saying that there are multiple ways to get a different slope. You can get super diffusion or
Yes.
transdiffusion
Yes.
by having a different,
Yes.
different phi.
Yes.
That's all I'm saying.
And,
Nothing more, nothing less. That's it.
But doesn't, I mean, so super diffusion, for example, 3/2. Right? That would be of interest for, that's Richardson sometimes. Do you know under what conditions that occurs? What does that mean?
You mean for what noise spectra?
Yeah. Or is that known somehow maybe?
For 3/2,
Or even anything which is bigger than 1 here? Now that's ballistic, that's already
Yes, but if you see it in late time, then
maybe even 1 year, right?
yeah, for long times, I don't know, I don't know. That's super diffusive. Short times, yes.
So they brought that up in the meeting, that in solar, the solar surface one actually sees often super diffusion. The question was, why is that?
I mean, it's hard to pose the problem in this context in any case, because you very often see super diffusion for short times, right? Well, in fact, you do for Brownian particles.
Yeah, you mean ballistic?
Yeah.
Of course, but that is not what you had in mind.
No.
in solar surface you have super diffusion for what? And for which quantity?
No, if you're saying it has to do with red noise.
Right.
No, he's asking you about the sun. I'm talking about something else. I don't know anything about the sun, but we've already established that.
No, but if the sun had not white noise,
I don't want to talk about, I mean, you know, you're looking at a system which doesn't have an initial value problem associated with it, so I'm not really sure what. We're talking apples and lug nuts here.
yeah. No, I'm just talking about what you are talking about. I mean, the noise, whether it's, if it's red, if it has a spectrum which as a function of time or frequency, of course, look like this.
I is always Gaussian.
That would be right. That would be red noise. Either something like this or even something like this. And now I was asking simply, does this make the diffusion faster or slower? Does it raise the exponent to bigger or you say it's not actually known, yeah?
Well, the power spectrum is red for a white noise process. So,
Yeah.
so that's the spectrum you get from this kind of analysis.
So we're talking
Kind
about
of
the case
red
with pi.
particle.
So this is the PDF of pi.
So maybe if the PDF of phi has a power and a tail, then something interesting happens.
That's right. Come on.
Yes.
No, that wasn't right.
No, spectra of phi. you
It's
mean.
yeah.
Yes.
Yeah, so if there's a non-Gaussian contribution to that, you could imagine a long time behavior being different. And there are experimental systems that show deviations from Brownian motion for a long time.
Is that sub or super?
Both.
Okay.
Both.
Because I
So
can imagine that you can be trapped, and that can be distribution of trapping times.
that's right. Right. So
And
it's
then-
a leading walk with a variable dwell time.
Yes.
Yeah.
Okay, then that is something you want to look further into.
I think it would be interesting if we can look at the actual simulation, and from the simulation find out the statistics of phi.
No, but you don't even know whether that equation applies.
Right, but if we assume it is true, for example, because alpha is well defined, right?
But how do you
Yeah.
Alpha is
how do you identify how would you identify the fossil phi?
Let me see. So alpha is a well-defined quantity, right? So if I now write an equation for time derivative of alpha, I will have something on the right-hand side. And whatever that is on the right-hand side, from it I subtract out minus alpha by a constant, tau alpha, which I can get from this, fitting this slope. And whatever is left is phi.
this position already talking about, so they don't have a solution equation so easy for this. It's an average over
Yes, this
all
is the average over.
positions, yeah.
So I guess phi will also be average over some scales. Right?
Yeah, maybe that can be done, but I think it's tough. Okay, other questions? Okay, so next week we have nothing on schedule yet. But we are also not many people here.
Yes, there is only 4 of us. 5.
Yes. And then on the week after we have Christoph speaking, and the title is still in the moment. hopefully.
Yeah, I'll give you that.
Hmm?
I'll give you the title.
Yeah.
No problem.
Good. Okay, so if there's nothing else, then thanks. So yes, we should. This should be. I remember I had it on my paper.
So which
We recorded massive particles.
So that's actually the
Sure, but
On multiple
Oh,
So let's follow ask what would be the relation of the
yeah, good.
The thing if you take basically this, you're in for your whole book.
So I
So,
saw.
if you do the following problem,
Corona
if you solve the equation, you solve the equation, you have a velocity field, and then out of the velocity field you solve the position psi is equal to u, right? And this is
and I want to understand what the position functions are the shortest time scale. And then what I want to analyze is the cumulative position.
That's a process of solution for some reason.
And if that's all I have, then the only thing I can do is say, well, what's the noise about?
So what you do?
This is a tracer, right?
On the time scale that I decide.
That's just a tracer.
Yes. But then what is your use?
Yeah, the thing is, use the unity from the temperature.
Yeah, but for the condensate, the velocity is not the full velocity.
But it's the velocity of, in your case, it's in your case you
Yeah, but then.
but if you use the velocity of
Yeah, but you really use the alpha transition. So that's your equation. And then you wait
So you've already, by definition, got rid of the question. So I only have then say, okay, I have X is function T, with the about some running mean, and then I want to produce what they call trend, which is the cumulative product of the data.
But then you use the beauty.
And then I will look at the variance of that relative polynomial. And that window, you think
No,
about
I have been
being
in
associated
Spain
with
in chemistry.
the time scale and the autocorrelation.
That's
What I
why.
want to do is for
Now
all
you're
sorts
saying,
of
this
time
is equal
scales.
to-
And I
you're
will
saying omega
be able to see the very long time behavior.
And then
So
just
it's
down.
Yes.
Yeah, totally, yeah,
over the large time, but the one each time window you have in and then you want to do
Then you have to agree. Then there is at least somehow suggested on the lambda effect. I mean, it is really,
this is, a methodology
Yeah.
which we're thinking about right now for
Is that the lambda or?
looking at.
no, Acker effect is,
And
as I said, there's an effect.
it gives you.
Okay, but this is wrong.
And he called it actually alpha, so from that point of view, it might be okay.
All the
I just think about the dynamo.
Yeah, right. Yes, but,
This is exactly what we want to get out of it. And that, if you.
but it's maybe not even that obvious that,
Then, what we can do is then go back and make the right model.
and I think you might want to do, but that's not so important.
No, no,
And then
no.
you can actually decompose it, you can say that let's say alpha is at the time scale.
Then it has a line on it.
That is, if you call it lambda.
And so that's my.
And then you have
And
you
the
just
quantity,
treat it like a
I would write it as-
Yeah, except it's actually an
I
anti-function.
mean, it's what I've just described is.
It's an anti-function because that gives you the condensate. You need to balance the anti-function with the real.
Developed by
Because it's unsavory, of course.
But you actually have to your molecular velocity, you have to real balancing.
and this is exactly
Chris is,
when you said this model
Okay,
is on now.
yeah, it becomes zero or negative. And the only thing is still positive.
So the whole thing will become zero
Notice,
at
when
steady
the
state.
actual observed time
Okay.
series
Before that,
isn't long
Before
enough
that,
for you to see what we're
then
asking
beta is
for
bigger
in
than
process.
that's the reason your thing was escape.
Yeah, right. That is.
That's not the reason, that's
Yeah,
an.
but I'm saying,
That's the answer. No, you're absolutely right.
But I'm saying it's okay to be unstable because that's how you grow the condensate.
yeah, but mathematically, if somebody wants to take that at face value,
In the data. So now we have
then do the simulation.
empirical
Evidence is not a close equation, right?
right?
So of course, this thing will blow up. What I'm saying is,
Exactly. So you use the numbers, we have the data. And so there's that approach and the approach of just viewing the
I
data.
don't think so. I think it's
this would be simply, so you have a negative, your negative. So it comes to the negative. But then it's being stabilized. So you have a, so you
Yeah, I guess we want to feel more
But I don't think, but K is easier because there's no model
It's
condensate.
literally
So K is
the
being always one.
It's not the application.
And this is one for condensate.
Yeah, it is.
So I guess the way to do
But that's okay.
the beta is actually viscosity, and then the density is gray, and then the curve.
I think it should be very straightforward.
I understand, yes. So if this in that sense, K and it would be for a higher case would be
Yeah.
again regular.
Sort of the theoretical stuff, because this model.
So I don't really know how you
I mean,
do
if you
that.
write such an equation, nobody knows that
Or
it's
it's
actually
analog.
K dependent. or applies only to one Fourier model.
So
So in order to do that correctly, you would have to either put a convolution here.
This one we should provide the
but-
No, you should have something which.
Then there's
lambda and beta you can constant in space.
If you want to apply it, you can do it.
Yeah, they can be constant in space, but if you have a convolution,
What's it to do with your topic?
the question is what is the kernel of plots here?
No, what is
Topic?
So in
Well, the speculative.
Then you can define.
or you can, what you're telling me, so you look, you go to Fourier space, and of course convolution becomes the multiplication of vector space. And now you tell me what is the properties of this beta in the transformation. So let's take here 0, 1, 2, 3 or something. And now this beta is clearly negative, you're saying. Which is good, makes sense.
Yes, we have something like
It's 1, yes, okay. So maybe it becomes even, you could in principle give going to smaller values.
all of us. And for.
But anyway, then
Beta is
We are
negative
not
at,
having a department.
at 0.
it could be something like this.
But we,
Beta becomes 0 no, but it maybe not, because it is itself multiplied by k once you know that, once you
The reason of that is when you have the level equation.
This is actually the thing I wanted to point to.
This is only at ku k1. Right, and then, so this whole thing can stay here.
No.
But then this part is also clear, k1. So this must be a constant.
It may have been nice to us.
Yeah, at one vector array, of course.
Okay, so what are the methods?
So all I'm saying is, when we do, if you do, of course, what is actually thinking, and very often nowadays we understand these as the convolution, which is even true, which is especially also true in a uniform medium, everything is homogeneous. It makes everything easier, of course, if you don't have a medium is uniform. Now we can go into Fourier space, and you, and the whole equation is the same, of course. Numbers are just replaced by ik. And all you have been telling me so far is that you actually really only know this equation for one particular value of k.
Okay, there are too many of them.
And now I'm saying, fine,
In that case, if you
and it will probably not be a big deal to extend your knowledge to different values of k.
So,
And once you do that, once you actually know this curve, which we can determine with the test field method and stuff like this, we can go back to real space and
I did my PhD in
Fourier transform back. So as an example, if you do a standard hyperturbo, it's nothing fancy, nothing related to 2D or something. We know that in Fourier space, our beta or eta or whatever has approximately this form. Has the form 1 divided by 1 plus k squared. Divided by something. But this is just the simplest possible case. Remember when Karl-Heinz was talking here? He had been talking about negative things. So he had a completely crazy form of equations, which are, I mean, they are correct. I wasn't looking at such a curve just yet. Clear camera, so you